We are going to use now intermolecular forces to explain some molecular properties. So here I have, let's write down the data that I have for boiling point. So this is isobutylene, and this is acetone. So here the boiling point that I have here, so I'm going to say BP is negative 6.9 Celsius, and here the boiling point of acetone is 56.3 Celsius. So what being asked to explain that is a property. So now notice that how can we explain that in terms of intermolecular forces? So notice that isobutylene, what we have is just carbons, and all of the bonds here, there's 2 bonds to hydrogen. Here we have 3 hydrogens and 3 more in this side. So the only force that we can have here, the only intermolecular force, is London dispersion forces, also known as van der Waals. And let's remember that these are fleeting dipoles, not permanent. So these are weak interactions. And this bullet point right here says this molecule is in the gas phase, its natural state. So this is very low, so meaning at room temperature, it would be a gas. Now, acetone, however, if you think room temperature being 25 Celsius at a lab, for example, this would be a liquid, relatively a low boiling point, but however, much higher than this. So how come this is a gas and this is a liquid? Having about a similar molar mass, same, here you have in place of this carbon, we have an oxygen, but other than that, it's very similar. So why is that? Well, what we have here in this molecule is that this bond is polar. Remember, we can draw an arrow representing the dipole, where this end is the carbon, delta positive, and there is more electron density towards the oxygen, so delta negative on that end. We can also do resonance structures and we'll show the same. But what this is that we have different types. So besides having London dispersion forces, because we have carbons and hydrogens, we will always have that type of force. But we have a force that is even stronger than that, which is dipole. And we can draw this molecule as being, say, negative, and let's say, I'm just giving it a shape, but that was not very good. Let's do this better. So delta negative, delta positive here. But we can definitely have other molecules organizing so that the negative is close to a positive. So in these are dipole-dipole interactions, we can simplify the drawing, say negative, positive, and these organized, say, back as Coulomb laws. So in these are stronger interactions. This is a permanent dipole. Here there is no permanent dipole, just fleeting dipoles, which is around the wall. So that explains why the boiling point is higher. The bond between the intermolecular forces between molecules of the same type are stronger, so I need to put in more energy. To give more kinetic energy to these molecules require that I have a higher temperature. Remember that kinetic energy, temperature is a measure of that, of kinetic energy. So that's what explains that trend in boiling point. Now let's go to this series. These are alkanes. So this right here is butane, and that will be C4H10. This is 1, 2, 3, 4, 5, so it's pentane, and it is C5H12, the molecular formula. This here is nhexane, and it is C6H14. So these are butane, pentane, and pentane, and hexane. So now the boiling points that we have here, let's see. Well, that's serious. So for butane, I have 0 Celsius. Then for pentane, my boiling point is, what is that? I believe it's a 26. I can see much my own notes. Okay, hexane. Boiling point is 59. Point is that we see that this is increasing as the molar mass increases. Remember, you do your molar mass based on your molecular formula. Molar mass is greater. And also, what is the type of intermolecular forces in this series? These are all alkanes. And all of the bonds that you have is carbon, carbon, and also bonds to carbon and hydrogen. So I don't have anything like a permanent dipole. I have only fleeting dipoles. So the only force that I have here in this case is London dispersion forces. And as we said before, these are fleeting dipoles. However, why is that difference as we increase the number of carbons? Now here we have a larger, say, surface area. So when you have molecules like butane, let's do a little bit of an overlap. Say that I have another butane molecule and it organizes this way to have, say, better interaction between two molecules. And now if I have, I'm going to have to draw it on the bottom, another molecule. Now I did it too close. That they can pile up, but now the surface area is larger, and if I go, as I go to hexane, larger. So there are more interactions. We're going to be adding up more interactions of the type London dispersion forces. And even though they are weak, this is additive. So we expect the molecule that is larger having more of those interactions, having higher boiling point, and that's the case, which we see here. So despite of being very weak interactions, the molecular mass is increasing, and also we have this surface area of contact being larger as we increase. And that is what makes a difference in the series below. So in the series below, I have pentane. Oh, that was 36. I didn't read it right. I have it in the other note. So boiling point 36. And here I have, notice this is, let's name my pack 1, 2, 3, and 4. This is 2-methyl butane. Notice here that pentane, in this case, here, this molecule is pentane, and the molecular formula is C5H12. What is the molecular formula of 2-methyl butane? It's actually the same. So it is C5H12. Finally, I have the other molecule right here is 1, 2, and 3. So it is 2, 2, 2, 2 dimethyl. In the pairing chain, notice, has 3 carbons, dimethyl propane. But what is interesting here is that it has overall 5 carbons in the same number of hydrogen. So these 3 molecules under share the same molecular formula, but they have different connectivity. Therefore, they are constitutional isomers. And now let's go and see what happens. So same mass, because they have the same molecular formula. So boiling point of pentane is 36 degrees, and that of 2-methyl butane is 28. I'm going to have to write it on the top. So boiling point is 28 Celsius, and for 2,2-dimethyl propane is only 10 Celsius. So let's erase this one here. So boiling point is 10 degrees Celsius. So notice that this is no branching. Same, remember these are constitutional isomers, so same mass. I'm not changing that, but I'm changing the branching. So here, as the molecule becomes more branched, the boiling point actually decreases for the same mass. So the mass is not an explanation here. What is that we have the same type of forces, London dispersion forces, but now the molecule cannot see, approach the same to interact the same way they did it in this series. Now the branching causes that these atoms can no longer organize the same way they change. So less of that a contribution of London dispersion forces. So the more branches the compound, the less we're going to have the London dispersion forces. Weaker interactions between molecules imply lower boiling point. And as we see here, pentane, it would be a liquid. The skin borderline between almost boiling at room temperature, right? Because boiling point is 25. But definitely 2,2-dimethyl propane, this is a gas at room temperature. So now we see that the molecular structure impacts a property, which is boiling point. And here we are seeing how the length of the chain, so molar mass, impacts boiling point, and also the branching, and also here, what is the difference when we have a permanent dipole versus having no permanent dipole?